I'll leave that to James, but yes, this
Okay.
material in some form will make it out, yes. And I will point out that the information I'm gonna talk is in much greater detail in the RFC, which is published as we speak. Or before we even started speaking. So just to, in a nutshell, we have users of our CPU compiler already at Google. And we had a goal, similar to what Kai was saying this morning, to be pragmatic. We want to evolve the XLA core stack in an effective way that takes people on this performance journey with us without kind of radically rebooting, starting over. And we believe that's a good thing because, hardware adoption on GPU seems to be where, the crazy red hot excitement is, but there's also a lot of potential on the CPU side and different people, different applications. Like we were talking about, CPUs actually have much better fit, and that's even true for in our case, in some cases. So we want to provide like just the right amount of support and make kind of like that strategic judo move to make what we already do more usable for folks like Intel and other library vendors and so on. I'm going to pop right into here. We did a lot of discussions with ARM and Intel and AMD and some others even. And we tried to form a picture of like what it would take to make life easy for our partners for which we rely so much on our performance. We also looked a little bit about, what would be useful for the Erie side. Stella just presented the Erie microkernels. We want to make sure those kinds of non-traditional library integrations are also served by what we're talking about. But as Amin was presenting, really the more predictable the pattern is to match, and the less that's a puzzle, and the less that's a moving target, and the less that it's hard to separate hardware from non-hardware independent passes, the easier it is for library vendors to hook in. And that has been sort of been done ad hoc before, where you go in tree and you find the right pass point in the pass pipeline, maybe through experiment, trial and error. And you decide where you want to go, and then you match your subgraphs, and then you replace that with a custom call, and off the races to you go. But we believe that if we do a little bit of a combo, cleaning up our passes a little bit, formalize that integration point, specify what you get or don't get in that integration point, work collaboratively to figure out like, well, what exactly do we mean by canonicalized and cleanup? Because maybe there may be some difference of opinions that may take some discussion in the RFC and outside. But once we have that, we think that will accelerate the work. There's also some quality of life things, like, when you find the subgraph you want, like in the case of the graph mode, if I understand right, you later on want to access that graph for other analysis reasons, but that graph has been lost in XLA. But if we could snapshot and, as we would say, staple that graph to the point where you attached your offload, you could then re-access that graph later. And that work seemed like a really obvious, useful thing that we would go on with. And then the RFC is actually already out. This conversation will continue in a broader sense outside this room. There's also some obvious performance problems we have and things we want to improve. There's kind of this hybrid eigen plus cuDNN model where we do blocking, pad, and packing with eigen, and then we do the kernels and 1DNN and Penpon, and you can speak to it already. Is working on a PR that actually unifies that.
Unifies.
Does the 1DNN for the whole combo, I believe.
I think it's more like RFC.
Okay,
yeah.
Apologies, overpromised. I need to do the opposite. But we've recognized that there's benefits to having 1DNN do more of that effort than splitting it into eigen. We've heard from multiple people that the threading is less than ideal, that the number of threads we allocate in our pool is kind of naively determined, and that we lack the ability to pin threads and set affinity appropriately, causing crash. And so that's something that we know we have a hole in, we need to work on. We also today, when we emit the thing that we then compile, we do that in one huge monolithic block, which creates a number of problems. For one thing, when you run in vTune, you get one module and one function call, and then you can't really attribute graph to that without adding markers or something like that. But if we break it up into units of compilation, then that should not only make the compiler compile quicker, have a lower memory footprint, but also make it so a profiler has less heavy lifting to do to visualize, knock on wood. And then I kind of shortchanged this, but we're doing some, and Eugene is ideally here for this conversation. We're improving the scheduling runtime aspect of XLA and using something we affectionately call Thunk++. Using that, and if we have broken our compilation into units of dispatchable work, then we could also schedule those and achieve some amount of interop parallelism. We don't expect that to be like massive gains like we get today with intra-op parallelism within the libraries, but there is some gold in them, our hills, and we can capture some of it that way. Here's a picture of it. So essentially the way you can think about it is the quote purple box is the pass pipeline in XLA, of which there are circa 41 passes that are passes, or some are repeated, but that happen in the CPU current flow. And we're proposing this integration point after the cleanup that I mentioned before, but not one, but two integration points. The top green box is the way that we do this today, where we say you write an HLO pass that does the pattern match capture custom call, or and additionally an MLIR style pass. That's still some TBD. There's some new work that needs to happen there, but we're piggybacking on similar work being done by the SPIMD team. And because the community loves to work in MLIR, and who knows, just between you and me, maybe we'll improve and update some of the other passes to be more MLIR. We're not going whole hog and rewriting the compiler, but we definitely have an eye towards MLIRifying or making our community happier by doing MLIR integration points. And then, like I mentioned, all this hangs together in a separate phase where we'll then be able to schedule these emitted bunches work, presuming that you comply with this ABI interface that TBD to be published by a separate RFC that Eugene will lead and drive. But that's kind of out of scope of today. Mainly, we're talking about the green boxes. The red stuff's a little coming later. And then last but not least, thanks. So there's the recap in record time. Questions before we do our kind of open share?
Yeah, I have one. So we have noticed that that there is a legacy path for XLA CPU, and there is XLA runtime, and which basically go through MLIR MLIR lowering path. So which one is going to be the final one?
None of them, I guess. Something in the middle. So even the MLR pass. So how will we do it today? It compiles a single function. So that apparently doesn't work well. So we want to split it into multiple functions and make it similar to how XLA GPU works. So XLA CPU today, you run your HLO passes, you identify fusions, you identify library calls, and then you emit basically traverse top-down HLO and emit everything in a single function. Roughly the same happens with MLIR. You convert HLO to combination of MHLO and some other MLR dialects, and you emit a single function. So we want to change that. First of all, you have this high-level HLO fusions. So for every fusion, you emit a separate function. It can be emitters, like we have it today in classic legacy pipeline. It can be MLIR. So it doesn't really matter. So the idea that for every fusion, you should have a pluggable code gen with some ABI that your kernel need to satisfy. So, and how exactly do you compile that kernel? It doesn't really matter because the input is HLO fusion, maybe stable HLO operation if you prefer MLIR to HLO, because it might be easier to get some stable bytecode representation. But in the end, the expectation that you should produce assembly with some ABI, and the runtime will call into that function pointer according to the ABI and will take care of launching it concurrently. How exactly we going to compile fusions into native code? to be defined. We will probably start with splitting the current, what you call legacy pipeline, into the blocks that will code-gen every fusion separately. But long term, we want to make it pluggable. So we should be able to reuse the malware passes if we need to, or Erie if Erie has some good things. Because this approach is very similar to how Erie thinks about this. So we don't code-gen the whole function Erie. So in the Erie side, you code-gen a tile, and you declare how many tiles do you want to run concurrently, and what is the relationship between tiles. And I think XLA will move in the direction. So yes, we'll start with legacy emitters. And legacy emitters is basically one parallel loop at the top, and that's it. And then we rely on LVM, auto-vectorization, unrolling, all of that. So this is probably the easiest path, like the initial version. Long term, we don't know what it will be. Probably a mix of things.
Okay, thank you. And you talked about interop, and interop will come up with some thread safety issue.
So what issue?
Thread safety,
Oh, thread safety issue.
because if some function is stateful, then it is we need to take care of the thread safety.
Yeah, I think right now the expectation that compute-intensive kernel, they are stateless. So you get your buffers as arguments, you get buffers for results. You can ask for a cache space from the runtime, and you will get it as an input, and it should be stateless. It shouldn't allocate anything. It shouldn't mutate any global variables, anything like that. Then the life of the runtime is much easier. But yes, if you need to put something stateful, yes, I guess we have to think about like what flags do we need to constrain concurrency. But in ideal world, it's just pure compute, buffers in, buffers out. You're not allowed to link anything else.
Can't trash the inputs.
Yeah, it should be a self-contained function pointer. Ideally, you don't even allocate anything.
Let me see. Sorry, one more question.
Oh, no.
Yeah, go ahead.
Time.
So sometimes we need some temporary memory allocation, and oftentimes this allocation is kind of fixed size over different iterations. So it will be nice if we have some memory pool allocator, like what we have in TensorFlow, BFC allocator.
Yeah, so I think this
So-
is the plan for.
I haven't seen the support in the XLA currently.
No, I think there's not. Yeah. Because right now we have it on GPU side. So high level passes, how it works on GPU. If you need some cache space, then in your compiler pass, you add a result, like a fake result, which is not a result. So something like that should be supported in CPU. So in your compiler pass for CPU, you should be able to require some cache space, and then the runtime will allocate it for you from the pool and just pass the pointer to the cache space.
Currently, we are using the fake thing for the scratch,
Okay.
and it is pre-allocated during compile time.
Yeah, I think this works nicely for GPU and should work nicely for CPU, and we will keep it.
And some of that, I think you go into a little bit of details now in the RFC, this idea that the analog on the GPU side would be the shared memory, but in your case, you would actually tell us the amount that.
Yeah, it's all like to be defined. We don't have with like concrete APIs, but the idea that shared memory on GPU, you can ask for the runtime to provide you like small scratch buffer for your tile, and runtime will take care that this is allocated from a pool on the same num node, or it is maybe likely in L1 because we passed it to the previous tile a few months ago. So something like that. So we don't want you to allocate new memory because runtime can place it much better than, well, because assumption that this compute kernel is stateless and it doesn't know anything where it runs on what thread with CPU, but the runtime should be able to pick the styles and schedule it efficiently based on some metadata.
Okay.
So in the simplest case, you just have one top level parallel loop and you can launch tasks on any thread. This is basically the current approach with eigenloop and parallel for. But we can do better than that. especially if you have some spatial relationship between data and you can do 2D tiling, 3D tiling, GPU like, and maybe give hints, okay, like this Y dimension should be scaled together. If you can. If not, it's fine to run the separate threads. That's roughly how, for example, MatMoves in TensorFlow and in Eigen implemented. It's like 2D problem, and Eigen optimizes that tiles from the same column ideally should be scheduled on the same thread because it's beneficial. But it's only like special case for MatMoves and convolutions because we know the data locality is super critical there. But in general, this is a very useful mechanism, and we will be adding something like that to the runtime. Because a lot of that was done in Erie, and they got it right. This, I think, is a good idea. Unified programming model between GPU and CPU. So we like that. We will add some of that to Xcelate CPU.
And maybe use words like dispatches for these hunks of work. It's a kind of a good word for these fused groups of things that have a sealed compilation and interfaces and schedulable units of work.
Yeah, basically a loop nest with some description how you should schedule it. What is the relationship between different tiles in this loop nest based on the locality properties.
But priority-wise, our feedback that we've heard is that interrupt parallelism is nice, but not like the prime mover in what's going on here. In fact, I think AG had said that it was actually counterproductive, but I think that actually was related to the threading issue more than anything else. But if we had to pick what we would work on first, interrupt is probably not it. And that's for the room and the RFC to discuss. Not that we won't get to it, but that's not what, in our mind, the biggest problem yet. From what we've heard.
Thanks.
In other words, there's plenty of parallelism in the per op that you can, within the library, exploit and keep the host busy, and there's not as much unused CPU cycles that could be taken up with interrupt, relatively speaking. That's what we've heard.
But I think one-to-one integration will be separate. So this is for code-gen integration. So what if you want to code-gen this block level function, or what if your library already fits nicely into this abstraction? Then you should be able to use that framework. Otherwise, custom calls, custom ops, this will be supported. So one-to-one convolution, it's fine to have it a separate custom call and offload everything to one-to-one. Then there is a question, okay, if one-to-one uses OpenMP and we're not going to use OpenMP, how that works together. But yeah, I think this is separate.
So as a part of thread pool, is it going to be only eigen thread pool or any other?
No, this will be an interface. So I think even right now you can implement your own thread pool, and interface is very simple. It just schedule task. I think it will be more complicated because we know that data locality is important. So maybe some data locality hints will become a part of thread pool interface. Because eigen interface and current thread pool interface inside Xcelate and the flow is super simple. Just launch this function anywhere, and thread pool has no idea. Can I run to the same thread? What are numerals constraints? But yeah, I think it should be pluggable.
Okay.
But it is very unlikely that we will support OpenMP, at least by default. So we will not support OpenMP at Google. That's 99%.
But you probably would like a way to plug TVB in.
I think we probably should borrow some ideas from TVB.
So if we implement our own thread pool, does that mean a custom compile, custom distribution? How will that work?
So I think the distribution, the styles distribution, will be part of the XLA API, and then probably part of the thread pool API. And then it's up to a thread pool implementation, okay, what the distribution means. Luminals, threads, and data locality. If you have multiple CPUs. So you want to offload this decision making to a thread pool. So default thread pool initially will be Eigen. But we should open API, so you should be able to create your own thread pool if you want to, and have enough information about task locality, data locality.
Okay.
So we heard about the D tensor, distributed tensor. And how is it going to be supported on CPU?
So
You want to have subnuma as a abstraction of the device, and we can divide into multiple devices. And we want to support the D tensor.
yeah, I don't think that we discussed that. I think when we think about details, I would think about different machines and data centers connected over the network. I don't think that we ever discussed NUMA. Yeah, I think it's nice to think about NUMA as it's a distributed system basically.
Yeah, we can also go to the subnuma.
Yeah, the problem that right now details it relies on send receive hooks, runtime support that sends the data, and the overheads just are much higher. So it's much easier to get the memory from the neighbor NUMA node than go through the runtime support for send receives. So it's not implemented for CPU. I don't think that anyone does distributed training. But if we would try to implement it on top of current integrations, that would be too slow.
Were you thinking like for training workloads or
Yeah, even for inference.
even for inference, really?
Yeah, I think
You wouldn't want to just do your own explicit all reduce or something like that between nodes and not do a distributed tensor, but do the basically manually do the distribution and the reduction.
Yeah, that is also possible.
I think it's nice if you can launch multiple Excel executables, pin them to the NUMA node, and just magically rely on communication.
So in that case, we would implement our own reduce operations that would be
Yes.
aware of the distributed processes on the same system.
Yeah, I don't think that anyone thought about this.
Yeah, we're kind of inventing this as we go along right now, but
Yeah, let's like
sounds like another-
about it.
sounds like a good RFC though. And we would love more folks to.
Yeah,
Authorize.
what's really the latency difference? Is it that huge that you need to think about that way?
I think it's easier to handle NUMA as a separate case. I mean, inside Google, we also have, for TensorFlow, we kind of have internal CPU NUMA device that handles the NUMA, but I don't think we put it in open source version.
Yeah, I think internally we do something for NUMA nodes.
Yeah, externally, I think we can do something else that's different from DTensor because of the big difference in latency in internode and out of the node. Yeah.
Yeah, so
So I've done something similar in TensorFlow where you use the multi-node capabilities and you just map the multiple nodes to multiple processes on the same machine, and then you restrict each node to be a certain NUMA node, if that makes sense. So it works with, I can't remember, it's a long function. It's the normal way of mapping to multiple GPUs in TensorFlow before DTensor.
Yeah, I think the problem that overheads in the runtime probably are so much higher than if
So
you just
all reduces would be too slow.
Or just like the heuristic to figure out how to effectively distribute and
and
how to
the
slice
allocator,
and-
member allocator will allocate on a random NUMA node. Yeah, I don't think that any of that. I've seen something in TensorFlow, but I don't think that it's fully supported.
like we would probably do less automatic and then more turnkey as time goes on. So probably, yeah, it would be more of a launch multiple instances with some amount of assistance code, and then we evolve towards something more automatic later, just riffing as we talk about it, yeah.
Yeah, if we look at high performance computing, usually the hybrid MPI OpenMP is to use OpenMP to handle internal NUMA thing and then MPI for cross node. And for here, I think it's the same because in NUMA node, we don't need that long latency for internal communication. So yeah, I
Yeah,
don't
like
think we
if-
should have, I think we should differentiate between communication between NUMA nodes inside the same compute node and outside the node. Yeah.
And one thing I like about MPI and similar programming models is like it's like back pressure to the programmer. It's like I'm not going to magically figure out how to subdivide and hide this
Yeah.
problem from you. Like you have to think multiple machines and then you develop your strategy and like how you want to split intra and interbox. And then I'll support that versus just magically make it work. At least when we're first starting with this idea, maybe later we can make it all turnkey. I don't know.
So yeah, I think right now we implicitly optimize for locality. For example, in MatMos, so if you computed the previous tasks touching the same block on thread 1, when the next task arrives, we pick the task that touches the same block. So we don't like use NUMA localities explicitly. We just hope that thread scheduling didn't change the core while we were switching between tasks. But explicitly think about NUMA as like distributed PGRT data thing. I don't think anyone Google does it.
And do we go till 5?
Yeah.
Yeah, we do.
Okay, all right. Well, we still have lots of time to go. I just want to throw out, you can read them here, but I want to just share these, what I was thinking when I wrote these, and we could talk about these or other things. I'm wanting to find out, is the definition of what a good canonicalized state is something we can non-controversially converge on? Or how and what we would want to talk about in that regard? Not that we have to solve it today, but that is one of my questions in my mind is how do we standardize this point? We talked about the tree reduction causing problems in softmax. I would love to kind of feel good about what should be above and below that line in terms of our passes. I'm also interested, and this is actually an RFC that AG said that you guys would be looking at is, the proverbial not wanting to turn hamburger back to the cow. Like, how do we know when we should reduce at that line? What should we reduce and what should we leave at a high level so you don't have to rediscover the higher level meaning of that? Threading we've kind of touched on already. And then last but not least, this is kind of more blue sky, but as we move and the world eventually gets to heterogeneous computing, is there anything that in our assumptions that will kind of break if we imagine a world where we've got mixed GPU, CPU all working on the same model at the same time? That one's probably the most speculative of the list, but or anything else anyone else would love to share.
We haven't thought about what is a good canonicalization, like as you mentioned. It needs some thinking. And I'm not sure what is the question about quantization, dequantization of.
So sometimes, like stable HLO, for instance, I don't think there's a softmax op in stable HLO, for instance.
Yeah, no, there isn't.
So, but what if there was? What if we actually just left it as a softmax op and then you didn't have to unwind that lowered sub op back into a stable HLO or back into a softmax? Like, how many of those things are there, MHA, et cetera, that really are reduced to too fine a granularity? And what do we do about that? Like, how do we, as the op world evolves, how do we make sure that we're not creating unnecessary work for you in doing that unmatching or pattern rematching business?
I think this is partially addressed by the stable HLO composite ops proposal, RFC.
Oh, okay.
So you can define, I don't know the details, but you can define your basically custom composition of ops that, okay, this is my fused MHA. If you don't support it natively, then we will expand it to primitive stable HL ops and we'll compile it. But it should simplify pattern matching. You find it what's happened to that.
But from JAX or TensorFlow or from the framework, it has to be converted into that composite of
Yeah, I think that is
that.
not, there's no, not a solved problem.
Okay. I think it is sufficient because this kind of most frequently appearing ops are not many. Like I think the set of this composite op would be small set of such kind of op. So it would be good if we have some composite.
That'd be like layer norm, FHA, softmax.
Yeah, something like that.
All element wise ops. And you're saying that we should be able to define that list fairly readily without having to. Like, that's not that big a surface area of a problem where we should be able to standardize on that.
Yeah. And if some backend doesn't support, yeah, go disintegration.
Disintegration, right? Yeah.
So for quantize, dequantize, op, currently in HLO we don't have any. The stable HLO has, but so is it there? If there is a timeline to have it in HLO?
Well, we had proposed that you write the RFC and then
Oh, okay.
we'll
Okay.
but
Sorry.
yeah, that's a good question. No, how long? I wish Eugene was here. Eugene Vermaco is obviously our stable HLO authority.
He's out sick today, but he joined on virtually this morning at least. Probably at the stable HLO breakout.
Oh, of course. Yeah. But we can take that as a get a feel for when that, how much work that is. And then you have your own heuristic that says, it makes sense to fuse dequant or quant into the map mole and then requant or unquant, dequant in the output. Like you have heuristics to take those ops and then decide, yes, this is a profitable fusion
Yeah.
in one DNN. Yeah. And is that whether you go down the graph API or the other, or?
For most of the cases, we don't need to do the graph API, but in most of the cases, it is sufficient not to go with graph API.
It's called stable HLO extensibility, and it's about this solving the pattern matching pain. I don't know what's happening with that, but I think a lot of people interested in NVIDIA, they have a bunch of libraries that also they have troubles pattern matching, fuse, multi-headed attention, implemented in Kubernetes. So yeah, it's not implemented, but I think it's enough interest, and I think it's public because I see some comments from NVIDIA, but I can't find the link.
You can follow up later.
Yeah, I'm taking it. Yeah.
Yeah. Yeah, I'll send upon your link to the doc
Thank you.
account.
What that brings to mind is, and maybe you already have this, it'd be great to have like an acceptance suite that says, like we said, we can enumerate the ops and actually have like this model. If I take this stable HLO in, I expect the library should match all that or some portion of that. And if it doesn't, then something is broken. But we've made the pattern unmatchable because of something we did. That would be an interesting way to kind of converge in what we're all doing, to have that reference, some reference model that should work. And maybe you have one already for TensorFlow, or like for the TensorFlow one, Dina, do you have like a regression test to make sure that it succeeds?
We have internal regression test. I'm not sure whether TensorFlow publicly has that kind of thing or not, but we have couple of models that exercises all this pattern, and every day, nightly, we have some regression tests.
Yeah, I wonder if there's a way to reuse that to some extent, you know. Cool, okay. Make so many notes.
Maybe we can ask other people in the room as well, maybe starting with Simon.
Actually, I just randomly picked the topic I'd
I
be
see.
slightly interested in. So I have like no exposure to XLA before, just coming from the MLR side. So don't know.
You were looking at Erie, right?
Yeah, actually, we are contributing slightly to Erie.
But so based on what you see in here, is there anything you think would be good to see in OpenXLA as well? Or what you are
Like in
using?
Erie, what do you interested in microkernels approach that they have? Or
Oh, actually, we are just how familiar with Erie. So there's this VM dialect, and then launching dispatches. Yeah, and actually, this VM dialect we lower to a limit C dialect to get rid of the
okay.
VM interpreter. So yeah, we are kind of niche. Yeah. So I'm not that expert.
So you're like the tiny Erie thing, right?
Yeah.
Yeah.
So I'm not that familiar with
Mhm.
CodeGen Erie side.
Got it.
Your partner was saying that you have CPU-based models that run on embedded systems that
Yeah,
need
yeah.
battery life of years
Yeah.
or very, very low power. But not needing massive throughput or low latency.
I think one of the problems that currently what's nice about XLA that we compile to a single CPU function.
Yeah.
It's super lightweight. You can just ship object file and that's it. And that's the XLA model. With this proposal, we are using this for tiny models. But what we see, yeah, I don't know how is critical. So once this proposal is implemented and we have this runtime. So right now, XLA program can be like hundreds of bytes. I know, for tiny program. It's super small and execution time can be nanoseconds. With its runtime, it will be microseconds at least. And it will be probably megabytes of runtime. Because we have AppSale dependency, probably protobuf will leak into the runtime because we can't do anything without protobuf at Google. So yeah, I think this will be the feature that we're losing from the current XLA. But for JAX users and large model training inference, it's not that big deal. Yeah, like weights can be hundreds of megabytes, even gigabytes. Then runtime, like 5 megabytes of runtime and 5 microseconds overheads. It's not a big deal. Yeah, we don't target microcontrollers and all that.
Well, the obvious question is, would it be massively hard to preserve that and have a choice? You can have the
Like
zero
have
runtime.
a flag to just have one thunk and run.
Yeah, if your whole model is a single thunk with dispatch, yes, we can emit function easily. But if you models multiple functions and library calls, then you have to do like the same thing twice. And it is unlikely that we will do it. Because I don't think that we have needs for that. Basically, the XLA runtime and XLA CPU today is compile everything through LVM to native code. And yeah, this is good for tiny models, but
Yeah, but how hard would it be to say we have XLA legacy mode that just still does that for? Or is that just,
oh yeah. Yeah, I don't think that we will be doing that.
I can imagine there's gonna be some pushback to that, right? And I
Yes.
think there's some people that are explicitly using CPU. to take advantage of this nanosecond, versus microsecond difference. So maybe that's something we should think about, is how do we have a fast track or how we enable these.
Yeah, I think for extremely small models, if you can compile a single function, then yes, we might be able to do that, this new framework. But that's not the focus. I think
We
the
at least capture a note though.
yeah,
We can do that.
yeah, I think the focus is large enough models, then third pool does matter, then concurrency does matter, and you have an operating system with a third pool, kernel, all of that. And not even, I think, on device. I think on device it will be a different solution. TF Lite, ERI based, no idea. But XLA doesn't have any plans to do some on device, like mobile phones or low power devices. I think it will be mostly about server side CPUs. Intel using Intel Tensor Cores in Intel AMX, something like that. Or if something shows up from what AMD does, no idea.
We actually have AMD on the call, so you're the next person we would like to hear from. Lakinder? Oh, I forgot that she has to type, right? Or
Not to put you on the spot. Oh,
Oh, okay.
yes.
then maybe we can ask Farhan next. Hi, Farhan. If you're speaking, you're on mute. Okay.
Okay.
Actually, on the other side of that.
One thing that seemed to kind of, the success of 1DN and the kind of the position you guys have taken where it's not x86 exclusive
Yes.
and that the ARM folks are extending it is really exciting. And I think a strategic and generous move from Intel's part. I'm kind of wondering how you think that would continue to evolve. And actually, I don't even know, I'm just kind of, how does it actually work? If you say you're writing an ARM extension for 1DNet, do you implement specific like ops, or do you have to basically implement certain levels of functionality and then it will dispatch to it, or how does that?
I'm not familiar with I'm not 100, so I don't know the details of
I can talk about it.
ARM is.
Okay.
Yeah, so they have different folders for the implementations of each backend, and in the folder they implement each of the main 1DNN primitives. For example, gem primitive for all mouse convolution, and reorder primitive, which is kind of like matrix layout reordering. So they have, each backend have their own set of implementations. And for ARM, there are actually two main contributors. So one is, of course, ARM. And in the implementations of those primitives, they link the code to ARM compute library for fast NetMelt kernel underneath. And the other contributor is Fujitsu, because they build their own ARM-based processors. So their top supercomputers, Fugaku, was actually ranked first in the top 500 for the past few years, but they just got dethroned recently. They are now second now. But yeah, that's an ARM-based processor, and they have an extension SVE 512 or something. So which is not supported in normal ARM processors. So they added that support to 1DNN too.
And I guess that makes sense how that would work, but does it also have this is really more of a cost model question, but does it have I know how to implement individual ops, but does it have like a heuristic that says, oh, I should do a fusion here, and therefore let me do A plus B instead of A comma B for code gen for arbitrary targets?
So 1DNN that dispatches to the framework. Like framework should decide what kind of fusion he wants to do.
Yeah, so basically it offers some primitive, like matmul primitive, which allow some post-op, which is kind of like a fixed set of element-wise operations that can be followed. So it's up to the framework to call this primitive and tag some post-op to it.
Yeah, okay. I
It
thought,
did provide some implementations.
okay, I had that wrong then. I thought that Oneian actually was matching subgraphs greedily and doing its own fusion
That's probably the
Optimization.
That is the one unit graph.
in
API.
graph mode only.
One
Okay.
unit graph model. Yeah, so they have some heuristic over which of the operation to be grouped together and to generate code for that. There is some kind of heuristic base, and it is more on trial and error base. There is no analytical model.
Right, no, it's empirical, right? It's or some, yeah, we're running, that's ongoing debate on closed, there is no closed form plug and chug answer to those questions, at least on modern hardware. Modern, non-boring hardware. Okay. And do third-party non-x86 vendors do the graph API also? Or is that kind of like are they starting with the,
So as far as know, only the x86 CPU and the Intel GPU is using the one graph API.
okay,
I can share the screen just to show the one DNN code just quickly. Yeah, so if you go to the one DNN repo and go to the source folder and then CPU, you'll see the implementation for each backend. They recently have RISC-V backend as well, although not many implementations yet, but you can go to AR64 and you'll see, yeah, their implementation for each primitives that one DNN offers. Yeah, and for x86, it's also a different set of implementations.
sure. And is that actually, oh, there's AVX too, I see.
Oh,
Okay.
sorry,
No, that's
stop sharing too soon.
And then-
Okay.
one topic we haven't talked about, we were really thinking CPU when we did all this work. But one DNN has Intel GPU support today. At least when I was at Intel, there were more than one GPU projects. But how does everything we've talked about fit into GPU? Is it a drop-in where a lot of the work we've done, if you targeted an Intel GPU, this would just work because you're just targeting one DNN libraries for GPU and, we're done? Or what if we wanted to expand what we've been talking about to be Intel GPU supported?
Theoretically, it should just work. Although in reality, the GPU team has to do some extra work with it.
Is it for the invocation of the kernels?
Yeah, I think
And then
the
data
assumption
transfer.
insulated the assumption that all the buffers, they all live on the same device. So if you try to run one DNN GPU inside XLA CPU, you will always have buffers on different devices, and XLA doesn't know how to move them. So it has to be a part of XLA GPU. And the device will have to implement some stream executive abstraction, I guess.
Marshal the data back and forth.
Like provide some kind of a stream event, some mechanism for launching kernels. So yeah, it will be no kernel launch will be probably unimplemented. So only library calls plus data transfers and stream event, memory copy. And I think that's it.
Well,
So yeah, the problem that
what?
everything should be compiled. So if something is not supported by one DNN, XLA should be able to compile it and run on Intel device. And it means probably SPIR-V, and we don't have any SPIR-V support. Erie has some SPIR-V compilation. So yeah, maybe we can.
Intel has LLVM to SPIR-V translator that they're using in their plugin.
Okay.
We can use it maybe, or just leave it to.
Yeah, the problem that GPU backend, it's very NVIDIA focused and it emits LVM plus
That's not
NVIDIA.
friendly.
Yeah, it's not really LVM, it's not really CPU. So yeah, that thing that takes HLO that can be met to 1DNN and converts it to SPIR-V friendly, like that Intel GPU can load and run. That part doesn't exist. I don't know like what's happening on the EE side. I don't think that it like also works there that well. Although SPIR-V welcome, yeah, I think it might.
That was working before, yeah, before HAL. I mean, like, there were ideas in that were done ahead of time of the
Yeah,
other
so the problem that right now XLA is always XLA executable is a single device,
one memory space.
one memory space.
But I mean, if you had the marshaling code added, I don't know, that's not the topic of this, but one reason we went down the path we went down versus, I mean, one of the alternatives considered is to use like Erie for CPU and XLA for GPU. Just in full transparency. But, you know, we wanted reuse. We want to have the past goodness be shared, and we don't want to have to do two radically different approaches. So like when Intel GPU comes along, we wouldn't want to have like 1DNN is completely different on CPU than GPU. We'd love to have like as much shared as possible. So I don't think it's too early just to see, you know, what would it take to actually take baby steps toward enabling that. And it's in the open and RFCs, et cetera, and we can, with whatever time we have, look at it.
Right now, Intel GPU team is writing an RFC of upstreaming some parts of their plugin code to OpenXLA.
Oh,
So that may be coming soon. I don't know. No timeline.
We should make sure that harmonizes with all this stuff, so we didn't miss anything or create problems. Oh, we're almost,
Sorry, I forgot to ask another important questions. So this is regarding but persistent compilation cache. JAX has some ability to use persistent compilation cache, and we try to use it for the legacy path, but it doesn't work. It just crashes. But the MLR based, like this CPU runtime, that actually works, but the legacy way of going, it doesn't work. So
Well, the problem that you can right now export compiled executable to all it's object file in the end, but we don't have a mechanism to load it back. And yeah, I don't know how hard it is. It was XLA CPU malware based. It's also very simple. We get an object file that we save on disk plus some metadata in protobuf, and we load it back. Yeah, that's not that hard to do it in XLA Classic. I don't know.
so nothing blocking to that path, right?
Yeah, I think if you want it, you can add it. Contributions are welcome.
and what's the use case? Is it to avoid?
Yeah, so some model takes very long time to compile. So if you want to run multiple times to do some performance analysis,
Yeah,
profiling,
They both like
it's kind of not a good experience. It's just kind of frustrating that it takes about a couple of minutes to compile to get
it is
that.
exactly the same LLVM org compilation and exactly the same LLVM execution engine thing. So it should be mostly identical. So yeah, it should be doable, definitely doable. I don't know, will anyone on our side will do that? Yeah, I think someone needs to open and take a look. I think it's like one directional right now. You can save it, but you can't load it.
And I'm probably saying a naively uninformed thing here, but if you just compiled with AOT mode on, would you not just get a binary? You
You
could run.
get back an object file that is compatible with some TensorFlow signature, but it's slightly different. So XLA CPU has an AOT mode, but it's a mix of object file and C++ header that you can link everything together, but it's very TensorFlow focused.
But it is also single threaded. I have noticed.
Yes, probably. Yeah, so
Yeah,
I think
it's only one thing to run. Like there's nothing to thread. Is this an ask that we need better AOT support for?
well, persistent compilation cache, we have it for TPU, we have it for GPU. It would be really nice to have it for CPU.
Is that part of the RFC or just a general separate?
Yeah, it was now discussed as just general usability. Yeah, so we enabled for GPU. JAX users like it for GPU. It is compatible with TensorFlow compilation cache. But well, no one asked it for CPU, so that's why no one implemented. But it should be doable. So I think we have roughly an idea how to do that, and that might be not that hard.
See, your fingers are furiously capturing that one pen point.
We're gonna need
So
to
right,
use
and that-
summarize.
sorry,
Oh,
Sarah, go ahead.
I was just commenting that we need to use Bard to summarize the notes.
Okay. So one of the other use cases, and I guess this is a pain point, is the compiler currently takes, in some cases, 150 gigabytes of memory, where during runtime it's less than 64. So it'd be nice to compile on one machine and then distribute it. Or then again, we could optimize the compiler.
Do you know who allocates that memory? Is it LVM?
No, we haven't gone into that. I mean, have you looked into that?
Okay, yeah,
We
one
got the same report from AG.
150 gigs. It's a lot.
Is there any chance we think that's, will be covered by the multi-compile
I
stuff? or-
suspect that LVM is a problem here, and LVM sees a giant function, and it associates a lot of temporary data structures inside process. But yeah, it would be nice to confirm. Maybe we have something simple inside XLA going on. Maybe we allocate something in a loop and forget to pre until the very end. Might happen.
Do you have like a contrived input we could repro? I mean, we know we have the problem, but we'd get it fixed quicker if we had like a,
Yeah, if you can get this, yeah, if
Yeah,
you
we can give some reproducer.
yeah. let's-
Yeah,
let's
because
do that.
yeah, we can get some allocation profile internally and
Yeah.
see.
You can
Okay.
use some Hugging Face models, GPTJ. I can send you links, but I guess that's a side issue. I mean, it would always be good to be able to have precompiled binaries to run.
Yeah, there's definitely two things here, but.
Yeah.
We shouldn't, there's no reason we need more space to compile than we do to run. Unless we're running a state machine or something like that, where there's no memory, but. Well, I think we've filled the time, and I think we all can reach each other for more questions, and please do open up the RFC and aggressively, comment on it. And barring any other things, I'll walk you over to happy hour.
Thanks.
Yeah, thanks for being, all of you for being great partners. This was a really enjoyable experience to go around and get your take, and you've informed so much of what we prepared that we couldn't have done it without you. So thank you.
Thank you so much, everyone. Bye.
All right, thanks a lot. Thanks for having this summit.
Thanks for attending.
Yeah.